small break, so I want to change to phenomenology. I want to set kind of landscape and describe some terms and talk about physics, and then I will come back again to some formal points. Maybe Darzena was also talking about this somehow aspects, but I will go fast now. Yeah, so, this picture of heavy-ion collision is usually based on some simple geometrical concepts. When you have two nuclei which are Lorentz contracted, when they collide, there is some overlapping region, and neutrons from this region are called participants, the other are called spectators. Then one usually, because the beam axis is privileged, then one decomposes all vectors into longitudinal parts parallel to the beam and transverse parts. So then one defines the transverse mass and rapidity and pseudo-rapidity. So rapidity is defined in this way. If you probably know quite well that this variable is additive under Lorentz boost. So if you make subsequent Lorentz boost along the z-axis, rapidity is additive. Like if you make, for instance, rotations around the fixed axis, the angles are additive. Usually the angles are, of course, not additive. Lorentz transformations have no simple rule form combinations. So this is the great advantage of this variable. Sometimes in the past people were measuring pseudo-rapidity, which is defined in this way, and this is really the measure of the scattering angle. And the difference is that in the definition of rapidity you have energy, and here you have the length of the stream momentum. You think that if the energy of the particles is large, so it doesn't matter, and these two quantities might be just identified. But in practice there are differences. I think this is really exactly the variable which is additive under Lorentz boost. Pseudo-rapidity is not. Well, what's also, I think, nice, I think at high energy and makes our life simpler and maybe boring from some point of view, is that if you increase the energy of the collision, then the central region becomes more and more barrier-free. So this is the net protons distribution in rapidity for different energies. So when you start with lower energies at AGS, then you see kind of Gaussian distribution. So you have really baryons placed at the center. Then if you go to SPS, then you start to see a dip. And then when you go to even higher energies, this dip is deeper, larger. So essentially, at the mid-rapidity, the baryon
Wojciech, could you take a little bit away the micro? A little bit. Try. Oh yeah. Try to adjust if possible.
The baryon is better, the baryon number density goes to 0, and then, so this is the place where one can compare really theoretical calculations with lattice results, because if you run hydron for this region and you use equation of state, you can take the equation of state from the lattice, and this is just the first principle input for hydrodynamic calculations. Now, if you measure transverse momenta and the rapidities of the particles, then you can make the decompositions in the angle, the azimuthal angle of the produced particles. So you can make Fourier expansion, you can have cosines and sines, or you can have cosines, but you can have cosines alone together with the phase. Yeah? So this kind of general mathematical decomposition, you have coefficients vk and some phases psi k. And these coefficients depend on the transverse momentum and rapidity, and they are called harmonic flows. And V1 is connected with kind of bouncing of two nuclei, they collide. So now this is the beam axis, this is the transverse axis. usually spectators are a bit balanced, and for them V1 is positive. So they go this final because of this here they go in this direction. But actually in the experiment you see negative directed flow close to mean rapidity. So it means that in this region where the hot matter is produced, you have kind of gradients which push the matter down stairs and upstairs. So this very small, very small kind of effect. Directed flow is measured, I think, in fractions of percent. But what is really important, and it was kind of the basis for the interpretation of the data is the value of the elliptic flow coefficients, V2. Usually, you know, this very, very popular plot. When two nuclei overlap, now the beam axis is perpendicular to the screen, and there is this almond-shaped region with hot matter. And then there is one argument used all the time which is wrong, which is like this, that you have pressure which is fixed in the middle, and you have the pressure which is here at the edge, so the gradient of the pressure in this direction is stronger, so you have more flow in this direction than in the opposite direction. So this argument is not completely correct, because usually when you have the collision of heavy ions, you have convolution of two Wood-Saxon distribution. So actually the gradients different from zero are only at the edge. But doesn't matter, still this argument can be used, because what happens here is that the refraction wave enters here and bounces back, and because here the distance is shorter, I think there is faster expansion in this direction. So I think this argument, okay, what should is a little bit different argument, but finally you have more matter going in this direction. This phenomenon happens at very large energies, where spectators, which are now shown in blue, they really pass away quite fast, and they don't make any obstacle here for this matter to go in this direction. At lower energies, spectators move with smaller velocities, and then you have more flow in the perpendicular direction.
Wojciech, but you believe that the system thermalizes?
No.
So this Wood-Saxon doesn't matter, because this is an initial state, and I think, at least I understand it, that the system is thermalized, and then of course you have a pressure, the gradient pressure is different in both directions. So I don't know how it is. Of course you are telling from the side of the person who is doing the simulation, okay, so you know it better. But,
no, the last lecture was about this, the matter doesn't thermalize, you know, but
No, I don't know that it thermalizes.
but you know, if you use Wood-Saxon probably, then it's difficult to introduce some gradients here or anything. Grażyna?
Since you are already interrupted by Krzysztof, let me ask you, why on the previous one you have had the spectators going down and up instead of being parallel? Yeah, here. So your spectators are just tilted to a lower direction or higher? How come?
Spectators, they go like this at high energies.
Yeah, but they should go straight, parallel to your arrows, not going down and up.
No, they, you know, spectators are really bounced like this, you know, we've seen that data, you know. And
Okay.
at lower energies is also like this. It's like, you know,
Okay, I
bouncing
thought you had some
like collisions of the balls somehow.
Is it electromagnetic effect or something different?
I think it's strong
This is
actually,
artistic.
yeah. Of course, in NA61 there is this activity about electromagnetic. Yeah, so maybe it has something to do with this. Yeah. So maybe you are right, maybe there is some electromagnetic contribution, but this effect is also seen at larger energies. I remember Star data also they showed.
No, I think the electromagnetic is when you have a particle which is in the forward rapidity, charged particles, then it's interacting with spectator matter. So it would...
So, you know, what's really interesting and kind of breaking even what the realization that you can have fluctuations of these initial conditions, and then you can have also other forms of the flow. For instance, because of new clouds, you can think that of them as just randomly distributed within nuclei. So if you have actual collision, they can be at different positions. So even if geometric picture tells you that it is ellipsoid, then it can be completely different shapes. So you have to make the Fourier decomposition of different really configurations. And in some cases, you have deformations which look like triangle, even for semi-central collisions. So there will be also some other harmonic flows, like the triangular flow, which are due to the fluctuations. So this opens the new activity in the field, because then you have to have also models which take care of fluctuating initial conditions, and then you run hydro event by event for each randomly generated distribution of nucleus. Now coming back to elliptic flow. This is really important because elliptic flow really is sensitive to the viscosity. There was a paper by Wojciech, published in 2007, so already 10 years ago, and here we see the dependence on the elliptic flow on the viscosity. So viscosity decreases. When viscosity increases, elliptic flow decreases. So V2 is somehow a measure of viscosity. Yeah? So I have already mentioned that the equation of state is somehow sensitive to the correlations to HBT. Because if you have first order phase transition, the system is quite long, the radii are large, in particular some specific ratio of the out radius to side radius should be large. So the correlation tells something about the equation of state. Elliptic flow tells us something about the viscosity. Of course, we have to make multi-dimensional plots now. This activity becomes more and more popular. This is named as the Bayesian estimates of the parameters of the Coulomb plasma. Stefan Baz is doing such things called proud. So you run dynamic codes, and then by comparing with the data, try to determine the equation of state and viscosity coefficients. Now, one comment about the QGP shear viscosity, whether it's large or small, because people also keep repeating that viscosity is small, but viscosity is not small. I already told you that what really appears in the hydrodynamic equation is the ratio of the shear viscosity coefficient to the entropy density, and because the entropy of the plasma is quite high, this ratio is also the ratio becomes small. Yeah? So this is just to entertain you for a while after lunch. There is a famous experiment started by John Mason. He passed away, I think, some years ago. And this is the pitch experiment. There is the funnel, and then you put the pitch. Pitch looks like a rock, It's like he will hammer and it breaks into pieces. So it really looks like a piece of rock. But then if you put it into the funnel and you wait quite long, then you observe some droplets which fell one after another. I think the time distance is something like 10 years. So the experiment started in 1927. The first drop was, after 11 years. The 8th drop was in 2000. And there is some story I took from Wikipedia. You can read that even now there was the 9th drop that touched the base of this experiment. With some interviews of another guy who took over the experiment. I think Mason, I think, got something like anti-Nobel for measurement of the viscosity of the pitch. The viscosity which can be determined from this experiment is 2 times 10 to the 8th Pascal times second. Then when you use some formula for the viscosity of QGP, then you get 10 to 11. So QGP is even more viscous than the pitch. But if you divide by entropy, which is enormous, then you get this result which is close to 1/4 pi. Another information about the viscosity is such that the shear viscosity divided by the entropic density depends on the temperature, and then you see many results from all kinds of models, theories, and then you see that one expects the minimum of the shear viscosity close to the critical temperature, implicitly. And then when you go with temperatures which go to smaller values, you expect increase. And I think this is related with the restoration of the chiral symmetry and also with pions, because pions do not interact with the chiral limited low energies. So simply, when interaction goes to zero, then we already know that viscosity goes to infinity. Yeah? So when you decrease the temperature, then resonances do not play any role, and then you finally deal with the pion gas, and actually with non-interacting pion gas. So then, for the non-interacting systems, we have viscosity which goes to infinity. So this somehow drop can be, not drop, increase can be understood. Interesting story is that the bulk viscosity behaves in the quite opposite way. So it has maximum at the critical temperature. And now there is a lot of effort in all these simulations which run event by event 3D hydro to determine bulk viscosity. So this is one of these from lines in section. Oh well, so this was the end of the lecture. I didn't finish before, and then I changed to another thing. So I want to say a few words about the Glauber movement. This is kind of opposite side of the reaction to the side was discussed by Radek. Because Radek was discussing the freeze-out. Glauber model is kind of simple geometric model for the initial stages. Of course, you can have some theories which are related to QCD, like glass condensate. You can use ADS-CFT correspondence. But the Glauber model is kind of simple geometric model. One has to know it, because even if you use more sophisticated theories, somehow you have to use Glauber model to put kind of microscopic model into this nuclear environment. So Glauber got the Nobel Prize in 2005, just after he took part in Fort Meter in Budapest. He was invited by Hungarian friends. Actually, he got the Nobel Prize in optics because he was somehow disappointed that nobody was using his ideas in the hadronic physics. So sometimes it's good to change the field. Okay, Glauber model really treats the nucleus collision as a multiple nucleon-nucleon collision process. Yeah? So you have two nuclei. Neutrons are moving inside. They are, for large nuclei, they are distributed according to the Wood-Saxon distributions. And then you have a nucleon which collides with other neutrons. And each elementary nucleon collision is characterized by the inelastic cross-section. Initially, the Glauber model was used for elastic collisions, and then it's natural to think that a single nucleon hits another nucleon a few times, because after each elastic collision, nucleon is the same nucleon. But if we allow for inelastic collisions, then of course there is some conceptual problem that after a single collision, this nucleon can be excited delta or can be destroyed and so on. But we don't care in this approach. Somehow we treat nucleons always as kind of the same particles, even if we include inelastic collisions. So the basis for this consideration is the Iconal approximation. This is the classical approximation to the angular momentum, and we can start with the amplitude we know from the quantum mechanics course for the scatter heat of two particles. The amplitude depends on the energy S, so this is the center of mass energy squared S, and the T variables, so these are among the sum of the variables. T is related to the scatter heat. And now, at large energies, usually we deal with very large angular momentum, so L is large, so we can somehow assume the classical relation between L, the momentum, and the impact parameter. So now we have two nucleons which collide at the impact parameter B, so P times the momentum is the orbital momentum. L is large, so we can add one half. Doesn't matter. And now, there is a mathematical property that if L is large, then these Lejeune polynomials can be given by this integral representation. So we use it, we substitute this formula here, and then we change, okay, not so fast. There is the picture how it looks in space, so we have z-axis, the beam axis, you have the target, one nucleon. There is another nucleon which moves like this. There is the impact parameter B, the momentum of the projectile particle is P, and the scattering angle theta. And then this expression, which appears in this argument, can be written as Q dot B, because you divide by P and multiply by P, so L divided by P here is B. Cosine phi is used to just express, to introduce the scalar product of two vectors, and when theta is small, then sine theta over 2 is just theta, or sine theta, you can neglect the 2 here. So PL looks very, very pretty. It's just the integral over the azimuthal angle of this phase. And then the amplitude can be represented as the integral over the impact parameter. So this is very convincing physically formula, because it can be used to express the total cross-section, inelastic cross-section, also elastic cross-section. The total cross-section is calculated from the optical theorem, so we take the forward scattering amplitude, so we take P equals 0, and then we get the total cross-section. Then we can also calculate elastic cross-section by squaring the amplitude and integration over the angles, but because everything happens in this transverse plane, the integration over the angles is just replaced by the integration of the relative momentum. We don't have to look into this in detail. These are just two amplitudes which were before just squared and integrated over angles. Yeah? And so then we get elastic cross-section, and inelastic is the difference. And now, the crucial point in this is that we have the cross-section which is given as the integral over the transverse space over the impact parameter two-dimensional space, and we have some factor here which can be interpreted as the probability of the collision. P of P is the probability that there will be inelastic collision. And then if you integrate, you just add all these probabilities, and then you get the cross-section. So P of P, which is given by this expression, so chi is just a phase shift, is the probability of having a nucleon inelastic collision. If you integrate it, you get the inelastic cross-section. One introduces so-called continuous function here, T of B, which is normalized in such a way that the integral over the impact parameter gives 1. This is just a convenient thing. So simply from the phase shift, we have the probability of the collision at the given impact parameter. If we integrate over the impact parameters, we have the cross-section. So these concepts are really very, I think, nice, intuitive, simple. And now, having under control nucleon collisions, we go to more complicated collisions. So we want to eventually to describe the collisions of two nuclei. And then for large nuclei, Wood-Saxon distribution is quite incidental, so we use this distribution to specify random positions of nucleons in the nuclei. I divided everything by the atomic number. So A is in the denominator here because I want to interpret rho as also probability distribution. So these are some standard parameters for the radius, for the skin, and so on, with typical nuclear saturation density. So this is kind of standard thing. And then with the distribution of nucleons in the nuclei, you can start building models of more complicated reactions. For instance, so the point A, it was what I have just described. We can change to the nucleon-nucleus collision. Yeah? So now we know what is the probability of the nucleon-nucleon collision. So this is this element. But now B is the impact vector between nucleus and the nucleon. So we have to introduce the nucleon-nucleon impact vector. So this is the red line here. So actually we have to look not at B, but SA minus B. SA is this vector, B is this vector, so difference is just this vector. I don't care about the direction because everything depends on the rank of the vector. So this T gives probability of nucleon-nucleon collisions. Then we have to just average over the positions of nucleons in the nuclei. So we use Saxon here, and this gives us the thickness functions for nucleon-nucleus collision. I'm talking about the probability. Strictly speaking, the thickness functions times the cross-section is the probability. So if I put sigma inelastic here and sigma inelastic here, then I have probability for nucleon collisions multiplied by the probability of describing the distribution of nucleons in the nuclei. So it's really simple. Of course, if you go to nucleus collision, you have to make this trick 2 times. And then everything is similar. One introduces the thickness functions for nucleus collision. Then we have the thickness functions for nucleon collisions with this combination of the vectors to get really the vector which defines the impact vector for 2 nucleons, and you integrate over the distributions. And this thickness functions for nucleus collision is also normalized to unity. So if you multiply this thickness function by the cross section, you have the probability you have average probability for nucleon collisions in nucleus collisions. So then one can use it in simple somehow argument, because for instance now if we treat all these collisions as independent, we deal with the binomial distribution. So we can, for instance, calculate the number of n collisions in the collisions of 2 nuclei with atomic numbers A and B. So this is just a formula from the binomial distribution. We can calculate the average number of such binary collisions, and this is just the product AB times the thickness functions times the cross-section. So if the nucleus collision is independent collision of nucleons, then this is kind of average number of such collisions. And you can play such games somehow. You can continue playing such games. You can calculate also the total probability of an inelastic nuclear collision. It's the sum over all n's from n equals 1 to n equals AP. Yeah? N equals 0, it means that you have no collision. Yeah? So if you sum all other probabilities, you have the probability for inelastic nuclear collisions. Again, using some simple formulas for polynomial distributions, using this expression. And then, of course, if you integrate this probability over the transverse plane, you get the total inelastic cross-section for nucleus-nucleus collision. So this is a kind of simple machine which allows you to calculate the cross-sections and for different collisions, and everything is more or less determined by the geometry, by simple geometry of the nuclei, and by the inelastic cross-section. One can calculate not only the number of binary collisions, but one can calculate also the number of nucleons which suffer at least one inelastic collisions. So such nucleons are called wounded nucleons. So this term was introduced by Białas and Krzyż in Krakow in 1976. I think participants were introducing at Berkeley, I guess. You can correct me, but I think the name participants originates from Berkeley. Wounded nucleons originate from Krakow. The difference is that participants can interact a lot. But the wounded nucleons are always the nucleons which interacted at least once inelastically. At high energies there is a small difference, but if you look at details, maybe there is some small quantitative difference. To calculate the number of such wounded nucleons, you may start with the definition of the number of nucleons in the nucleus A, just using again the thickness function. Thickness function is just a distribution which is kind of squeezed in two dimensions, two transverse dimensions. So in other words, it's projected distribution. And so if you make integration over the transverse space, you get the total number of nucleons. And now, if you have the thickness functions times the element of the transverse area gives the probability for having nucleon in this position. And then this probability can be multiplied by the probability that the nucleon from this nucleus at the position S collides one or more times with the nucleons in B. So we again use these simple formulas from the previous slides, and we convolute this expression with this, and then one gets some expressions. We don't have to go into details. What's important? I think the wounded nucleon model is quite famous. It doesn't work quite well, but usually it gives very good leading order, I would say, approximation to many observations. And I will now tell you some general attitude in the community, or just. So this attitude is like this: that if we look at the processes at very high energy, so if we look at productions of jets, then we think that production is really incoherent, and then everything should scale with number of binary collisions. So this is kind of very general argument. Nobody derives this probability. But this is kind of simple argument that if you have large energies, then you have short wavelengths, then there is no interference, everything should be somehow counted as independently. So then, if you have productions of jets, heavy quarks, then there are some ideas, general ideas that hard processes should scale with the number of binary collisions. On the other hand, if you look at the production of soft particles, then experimentally you see that it's very close to, I think that it scales with the number of wounded neutrons. So you have two separate scalings. Hard, large PP particles are produced kind of in proportion to the number of binary collisions. Soft particles are produced in proportion to the wounded neutrons. As I mentioned, somehow the wounded core model doesn't work quite well. So there were some ideas that the particle production is proportional to some linear combination of the number of wounded nucleons and binary collisions. quite recently there are new developments that one should use the wounded really quarks and then the production of particles scales with the number of wounded quarks. So there is a series of papers by Mike Tannenbaum, my friends, and from Krakow here. So there is a lot of activity here. So this has something to do also with the structure of the proton, that there might be some hotspots and so on. So this is related with looking for some structures even in the proton. Yeah? So this, well, and so one slide about the nuclear modification factor, because this is what is shown very often in the data. And this is exactly related with this general idea that if you have the production of hard particles with large BP, that this production should scale with the number of binary collisions. So if you have the productions of some particles in the collision of two nuclei, A on B, and then you look at the density in some element of the phase space, and then you divide this by the number of binary collisions, and then you still divide by the number of particles which is produced in proton-proton collisions, that you should get 1. So this kind of measure somehow whether the collisions are independent or not with respect to these hard particles. So I think maybe Grażyna was showing this modification factor. I guess you showed. I didn't see your slides, but this is very popular also experimental, I would say, tool. One thing I want to tell you somehow, which also caused somehow some effort for me to understand, is that physicists do something like an inclusive cross-section, and this is exactly, this leads to, this is really the number of particles which are produced. You know, when you think about the collision cross-section, usually you think about some probability of some event which is normalized to the size of incoming particles. But if you look at the pions and you don't care about other particles which are produced, then actually when you use this expression for the cross-section, then you have some extra integral over the states with extra particles. And if you do this integral using somehow ideas that they form the complete set of states, then you see that this inclusive cross-section is really proportional to the number of the produced particles, and the coefficient is the total cross-section of the production. So if you, so the inclusive cross-section divided by the total cross-section is just the particle density. I think this is, I tell you this from my own experience, that it cost me really some time to realize it. Maybe it's obvious, but yeah. So this is kind of general setup which is related only to the geometry. And now coming back to hydro. Well, so if there is observation that the production of the particles is proportional to the number of the wounded nucleons, so you can calculate the number of the wounded nucleons in the transverse plane, and then you can use it as the input for the hydro. Yeah, so this is this, I would say, traditional Greek approach that having established the density of wounded nucleons in the transverse plane, we were saying, okay, so this will be proportional to the entropy density, which are here denoted by sigma. And then we can start with hydro, perfect fluid hydro, with such entropy density. The coefficient will be fixed by fitting the data and the normalization of the spectrum. And of course, this is what I was telling you before, that if you run perfect fluid hydro with such input, and we initialize hydro at short time, then we implicitly assume that matter is thermalized. And the success of this approach brought us to this idea about early thermalization. But if you switch to viscous hydro, as I was discussing in the first lecture, then you immediately see that it's not the assumption about early thermalization as we now see it. Some remarks about this combination of the wounded Newton density with binary collision. So this was in the paper by Nardi and I think Imakarziev. So you can try to get better description of the data using such mixtures. Now, I think there is some trend to replace these mixtures by wounded quarks, for instance, or some hotspots and so on. Okay, so this was, I think, to complete the stage, I think, and it's a kind of complementary discussion to what Radek said. Yeah? Because this is just a simple model for initial state, just referring just to the geometry of the collision, and then if you combine this with some concept of wounded Newton model, that the wounded nucleons or participants really determine the production of the particles, then you can immediately switch to the perfect fluid dynamics and run the codes. Yeah. So this kind of natural, very popular approach, which was applied at week. So coming back to Heidel. Perfect fluid is, as I already mentioned, is based on the conservation of the energy, momentum, and also of the baryon current. But in the central region, the baryon current can be measured. So we have 4 equations for 4 unknowns. And this is quite universal. Again, these plots show you that the baryon density decreases. I have one plot because from old times, which discusses the impact of the equation of state on the evolution, hydrodynamic evolution. Because now I think this issue is kind of renewed and discussed again. This is something to the relation with HBT. So what we did some time ago, we just constructed the equation of state taking the lattice data at large temperatures, and we combined with the results of the hadron gas for the sound velocity. And then the simplest interpolating model is shown by this curve number 1, the red curve. And actually, it was quite surprised that when you look at the sound velocity for 2 calculations, then you the approach. And then we can play some games, we can modify, we can try to make a dip here, which is kind of approximation for the first order phase transition. In the first order phase transition, the sound velocity drops to 0 because the sound velocity is the derivative of the pressure with respect to the energy density. And if you have the first order phase transition, the pressure doesn't change. And energy density changes. We have discontinuity, and then the sound velocity drops to 0. So we had some idea to study the effect of having the soft point here, and then we were just looking for the sound velocity squared as having such dips. So we looked at this blue dependent, blue and green. There is some condition for the sound velocity that if we want to decrease it here, we have to decrease it here, we have to increase it here. Because, when temperature is the only thermodynamic parameter in the theory, then all functions can be expressed by the other function. Using thermodynamic relations, you can just express entropy density by energy density by pressure by the sound velocity, and so on. But there is only one problem, that there are integration constants, and they should be arranged in the proper way. So, for instance, if you use sound velocity from here, and then you have to get the proper entropy density here, which is determined by the lattice calculation. So, this was the reason why we somehow had this increase here for the cases with the dip here. And now, these 3 kind of temperature dependencies of the sound velocity correspond to completely different evolution of the system. So now the 3 figures show the space-time diagrams for the temperature. So they show this is the contour plot of the temperature. So this for the canonical case, let's say 1. The initial conditions are the same. Yeah? So if you just make this cut along the time 1 here, so they have all the same profiles. But now, if you go to a deeper and deeper deep, then you see that the evolution is longer. You see, for instance, here we came to sort of critical temperature below 10 fermions over C. Then, if we have here 1, then it's more than 10, and it continues to grow. Yeah. So, and this can be controlled by the HBT calculation. So the equation of state is somehow sensitive to the HBT, or HBT is kind of probe of the equation of state. On the other hand, elliptic flow feeds viscosity. Okay, now I have 2 sections about very traditional approaches, hydrodynamic approaches, about the Landau model and the Bjorken model. I think they are important because people all the time talk about this, and it's good to know what is really inside of those models. The Landau model, okay, so the Landau model is one-dimensional model without any Bose invariance. And what Landau and also, I forgot. Okay. What Landau and his one collaborator, Kalatnikov, yes, realized that one can really change from 2 partial differential equations of the first order to a single differential equation of the second order. So there are 2 equations for one-dimensional evolution for the temperature and the longitudinal flow. So like T and U3. And then when you study this equation, you see that from that you can get the condition that the product T times the street velocity should be a gradient. Yeah? The flow should be a potential flow, so one can introduce the potential phi L for Landau, the product of the temperature and the pore velocity are given as the gradients. Then, so this is the first step. The next step is that you make the Legendre transformation and you change from the potential phi to the potential chi. And then, let's not go into details, you find the equation which is just a single equation of the second order for chi. And for fixed sound velocity, this equation is the equation with constant coefficient. Yeah? So actually this is the version of this telegraphist equation. So they knew how to solve it because they knew how to solve this telegraphist equation. And how this is done, I think, in practice. So very often it is said that in the Landau model you assume that two nuclei collide and they stop. And this is really true. So the picture is like this, that you have complete stopping. And of course at high energies this is not the case because I showed you that the Baryon number is really redistributed to larger rapidities, and in the central region there is no Baryon number. So in this picture is opposite. You have kind of stopping. Everything stops in the volume which is determined by the contracted volume of two nuclei. And then what happens is that there is the rare diffraction wave which enters this system. Here I use the original notation from Landau, so the center of the system corresponds to the z coordinate equal to minus L. That is some distance, contracted distance or size of the nuclei. So we are interested, because of the symmetry, only in the region which is larger than z equals minus L. And the situation at the beginning is like this, that there is a refraction wave which enters the system. So the edge moves out, actually the edge moves with the speed of light, and there is the refraction wave which enters with the sound velocity. And then when this refraction wave enters the center, it bounces back. And then you have, somehow you have to combine two solutions. There is this refraction wave which was bounced back in the middle, and then you have refraction wave which always describes the system at the edge. Yeah? So the main idea was to put everything consistently and to combine the solutions smartly. Yeah? So this was achieved by Landau and Kalatnikov. And then there is something which is not completely, I think, no, but there is a kind of invariance in the Landau model. Although people usually say, okay, Landau model is typical invariant model. So actually, Landau in his paper says that the freeze-out condition should be given by this condition. T squared minus D squared equals RF squared, so some freeze-out radius squared. And this freeze-out is equal to 2 times the radius of the nucleus. So this is exactly, so of course this is hyperbola of the proper time. Yeah? So RF is just the proper time here. So this was this idea, which is kind of boost element, this invariant element in the Landau model. And then if you have the connection between T and Z, then you have also the connection between the temperature and the rapidity. Usually when you start doing the calculations in one dimension, you have two independent variables. You have time and the space coordinate Z, so T and Z. And then you have temperature and flow, like the longitudinal velocity as the functions of T and Z. If you make the Lejeune transformation, then the roles of those parameters exchange, and then everything is a function of T and longitudinal flow. So if you have the condition between T and Z, then this can be translated on the condition which relates temperature and the flow. And this leads to this formula, which introduces some exponential. And there is some parameter L, which really is kind of trace of introducing this parameter Rf here. So L, capital L is log Rf over delta, and delta is this contracted size of the colliding nuclei. And then when you have T, then you raise it to the power 3 to get entropy, because Landau also assumed that the masses are zero, so everything here is just the gas of massless pions, all that. And then when you make expansion of this exponential, you have Gaussians. So this was the model for proton-proton collisions, which was introduced in 1950s, and so this was already the model for hydro in small systems, I would say. And there was this Gaussian distribution. I think Landau knew probably that there are Gaussian distributions of particles which are produced, and he could really get it from these hydrodynamic models, which was a great success. In the 70s, Landau model was quite popular. This is the distribution of the pions, because pions form this matter which is produced. And now we have to look at this carefully, because in this model, baryons really stop, and the pions are produced in such a way that they are described by the Gaussian distributions. And if you look at the data from Rig and you look at the rapid distribution of pions, of course you have very beautiful Gaussian distributions of pions, and also at the LHC. So these Gaussian distributions are quite popular, and they seem to be quite universal for the rapidity distribution. So many people think that the Landau model is, how we say that forever or something like this. Of course, there are these assumptions about the stopping, and we know that the stopping didn't take place in such highly energetic conditions. But this kind of interesting thing, with the stopping of neutrons, of two protons, you have Gaussians. Yeah. So I think this is one of the reasons that people talk all the time about this model, not only because it was invented by Landau, but this Gaussian distribution is quite, I would say, characteristic. Okay, on the other side we have Bjorken model. Actually, I should have written that the Bjorken model was also invented by other physicists, including Rudi Huama, and I think also Gorenstein and Sinyukov. The idea is to use concepts of boost invariance. So the system
By Larry Mark-Levin.
Larry also. The first was probably by Rudi Huama, but the paper by Bjorken had some advantage that it contains some estimate of the energy which can be produced in the condition. So, of course, Bjorken did other many important things. So this is attributed to his person. So the boost invariance is, of course, the idea that if you make the transformation, Lorentz transformation, the Lorentz boost, then the system doesn't change. This idea can be really very high energies, because if you think that you have two nuclei which collide and they move with speeds which are close to the speed of light, so if you make the boost, the initial condition is practically the same. Yeah? So at very high energies you expect that in the central region you have kind of boost invariance. I mentioned that rapidity is the additive variable if you make Lorentz boost. So it means that if you can measure the rapidity difference, it's invariant quantity under Lorentz boost. So dn over dy should be a scalar. So if you have dn over dy measured in one system, the shape is the same in other systems which differ by the Lorentz boost. So this is why also we always plot such distributions, because if you measure it in the laboratory frame, then it has the same shape as in the center of mass frame. You can also maybe think here about this Gaussian. You know, when y is much smaller than L, then exponential is just constant. So this also gives some kind of flat distribution to some approximation in the central region. Well, so the idea of Bjorken was just to really use the concepts about the boost invariance to construct the hydrodynamic model. And boost invariance implies some conditions for different quantities. Depending on the Lorentz character of some physics quantity, there are different, I would say, forms which are imposed on this quantity. So all scalar functions of space and time should depend on the proper time. So this is more or less obvious, because this is like independence with respect to some rotations. We have to get rid of the angle and introduce the length of the vector. In that space-time, the interval plays the role of the length, so all scalar functions should depend on the proper time, so the square root of t squared minus z squared. The form of the form velocity is less obvious, but it should be proportional to x mu, to the four vector which describe the position of the fluid. If we demand that at z equals 0, this space part of mu is 0. And then you can do some algebra to calculate the divergence of your mu, and then you can use the perfect fluid hydrodynamics to derive very famous equation for the entropy conservation. This equation already appeared in my first lecture, and it has very simple scaling solution. So entropy decreases like 1 over proper time. So if it's conserved for this invariant expansion, the entropy should decrease by 1 over the proper time. And then energy density fulfills this equation. and this can be also easily solved. Some comment? And? Okay. So, for instance, if the sound velocity is 1/3, then energy density stays like 1 over tau to the power 4/3. Okay, so I can maybe stop here, yeah. Or maybe I will come to. Is really that end or somehow like a few minutes, 2, 3?
You have 2 minutes, I think.
Okay. So, so this great success of Bjorken model was that entropy is conserved, and it fulfills this simple scaling rule. Then you can observe that entropy per unit rapidity is conserved, and then relate this entropy density with particle density. And this allows you for some estimates of the initial energy density. And whatever you do with such estimate, you get energy densities which are larger than energy density in the center of the nucleus. So I think one argument, some people ask about arguments for the quark-gluon plasma. It's obvious that the systems which are produced at such energies, they do not consist of hadrons. Hadrons have sizes, and the energy density which comes from simple arguments like this tell you that this energy density is at least 1 order of magnitude larger than matter. So at the beginning of such collisions, the energy density is really large. Right. Okay, so these were just two, simple models, one-dimensional models. Then there is one paper, I think, which is very beautiful. This is, I am telling you from many reasons. One reason is that Jean-Paul Lezo is here. The second reason is this was not my first paper I read in my life. I had to study it. So this is the paper by Bang, Freeman, Lezo, Swoje, and Schir, where the Bjorken model was generalized to include the transverse flow also. And then, of course, there was development to have more and more realistic models. 2+1 means that we include non-trivial transverse expansion. So Pasi was here, one of the pioneers with Kolbein, Sustanen, Voloshin, Kini, Szłowiaka. Then 3+1 models appeared. And then somehow this activity with perfect fluid slowly stopped, and there was the change to viscous hydrodynamics. So I think it's now a really good time to stop.
Okay,
So thank you.
okay, there's time for 1 or 2 questions.
I think you remember it, that Marek Jaśnicki was always using this Landau model. And one of the predictions of this Landau model, if I remember, is that the number of charged particles per unit rapidity scales like square root of S.
Yeah, but this is from the Fermi model. This is actually from the Fermi model.
Okay. So, and it works in a sense. Roughly.
So actually this was in the Fermi wrote first some model, okay, I didn't mention, but this was from the Fermi model.
So it was not coming directly from Landau model, Landau hydrodynamics.
So the chronology was, there was the Fermi model. Fermi assumed that, Fermi, the expectation, in the 50s was that if you have more particles, then the probability for production of such event is less probable, because this was the experience from electrodynamics. Because the coupling constant is small in electrodynamics, then it's less likely to produce many particles. When strong interactions started to be studied, then people realized that there is this phenomenon of multi-particle production, that you produce many really particles. Then Fermi somehow had this idea of the dominance of the phase space. He said, okay, we don't know really the interaction, but the probabilities are determined also by the phase space. So let's take this matrix element to be practically the same for many processes, and consider the dominance of the phase space. And then, in the end of his famous paper from, I think, 45, was kind of introduction of this thermal model we use, the most popular version, and then there was also this scaling with the energy. Then there was the paper by Pomeranchuk who was arguing that Fermi was wrong because Fermi assumed that everything happens in one fixed volume, but the system should expand and freeze out. So this kind of paper, I would really love to write because I think this is the paper without any equation, no? If I remember well. I think probably maybe there's one equation or something that compares the two cross sections. And then Landau took this idea seriously with Kalavnikov and they simply saw this paper inspired by Pomeranchuk. Yeah. So I think Gazdicki is somehow based on this kind of series of traditional developments by famous people.
Seems that data are also not so far away from such a scale.
Any other questions? If not, then let's thank Professor Florkowski again.